Welcome, everyone, to this pre-recorded presentation being offered through the Institute of World Culture, a nonprofit educational institute dedicated to lifelong learning in the promotion of universal brotherhood. The Institute is solely supported through donations from folks like yourself, is located in Santa Barbara, California, and holds live events like this one on a monthly basis, and also a weekly study group. IWC has recently started streaming events online at this YouTube channel, which undoubtedly you know about since you are viewing it. And links to upcoming events and lots of other information about the Institute and other cultural and educational venues can be found at its website, www.worldculture.org. And one can also find there sign up for the monthly digital newsletter in order to be sure not to miss any of its programs. The 10 aims of the Institute are articulated in its Declaration of Interdependence, which provide a foundation for all Institute programs. Aim number 6 is particularly relevant to today's program. That is to promote forums for fearless inquiry and constructive dialogue concerning the frontiers of science, the therapeutics of self-transformation, and the societies of the future. Because science is one of those fields of human knowledge that impacts all of us and which seems to be hourly undergoing transformation, we have under this theme umbrella a special program to be presented in 3 parts by Russ Lewin called New Visions of the Vastitude. The first part is Eyes on Mars, the Mars rovers and helicopter. The second, Eyes on Earth, the 25 Earth-orbiting satellites. And the third, Eyes on Cosmos, the James Webb Telescope. Today's presentation will feature the currently active rovers on Mars, the data and images they have collected, and the first flights of the Ingenuity helicopter, including the most recent videos NASA has made available. So hold on to your seats. Our presenter, Russ Lewin, is particularly suited to be giving this talk today. He is a recently retired teacher of math, science, robotics, and videography at Santa Barbara Middle School, where he taught for 29 years. And Russ is well known in the community as an energetic and knowledgeable teacher on many fronts, who is deeply interested in the betterment of humanity and planetary welfare through the right application of scientific knowledge. Russ is also a longtime member and former president of the Institute, who has given dozens of fascinating and educational presentations on science and technology, including several over the years on the Hubble telescope, both the imagery and the scientific discoveries that have resulted from it. He's also given many other presentations on a variety of topics as diverse as the symbols of the American Revolution, the emerging revolution of artificial intelligence, science and mathematics in Hellenistic culture. He gave a Founding Day address, I think it was in 2015 or so, on the American explorer John Wesley Powell. And in 2014, with his wife Jerry Lewin, he gave a presentation on the keystone species of Yellowstone National Park. In addition, it is no exaggeration to say that Russ has almost single-handedly developed Concord Hall into a recording and live streaming studio with the latest technology and capabilities for both recording video presentations, group discussions, and also podcasts. So we are indeed very fortunate to have Russ presenting for us today on New Visions of the Vastitude, Eyes on Mars, the Mars rovers and helicopter.
Inside the wheel of the Perseverance rover are etched 2 significant symbols. The rectangular track is a symbol of the rover and the technology that runs it. The double spiral represents DNA and is meant to acknowledge that all technology and all innovation comes from the humans that worked on the project. These are the people who were involved in designing, building, and landing the Perseverance rover on Mars on February 18th, 2021. Yesterday was the one-year landiversary. Perseverance is persistence in doing something despite difficulty or delay in achieving success. Thomas Edison said, "Before I got through, I tested no fewer than 6,000 vegetable growths and ransacked the world for the most suitable filament material." Lao Tzu points to perseverance as a principle of nature and says, "Water is the softest thing, yet it can penetrate mountains and earth. This shows clearly the principle of softness, overcoming hardness." Curiosity, a strong desire to know or learn something. Consider this. If you stood at the same spot and at noontime every day you took a picture of the sun, you would come up with something that looked like this. This is called an analemma. However, if you stood on Mars in the same spot and at noon every day took a picture of the sun, you'd see this. So Mars is a part of our solar system, but different in many ways. Both of these are referred to as analemmas, from the ancient Greek word that means support. Scientists always need to ask themselves, how can we unveil nature's great secrets? How can we turn ourselves into the key that unlocks her many doors? How can we generate true open-mindedness? Welcome everybody to today's presentation entitled New Visions of the Vastitude. This will be a three-part series, starting with today's presentation on Mars and the Mars rovers. The second installment will highlight the more than 25 Earth-orbiting satellites that monitor the complex biological systems of our planet. And the third installment will explore the newly launched Webb Space Telescope that will peer all the way back to the beginnings of the universe. Our hope is that this investigation will strengthen our understanding of the larger picture so that we may live more harmoniously and peacefully in our daily lives. Albert Einstein, who was a tremendous inspiration to science and probably to most scientists, made many discoveries that altered our understanding of the principles that guide the universe. He said that all religions, arts, and sciences are branches of the same tree, and he always expressed the need for individuals to think originally. He even said the only real valuable thing is intuition. Mars. What do you notice about Mars? It's red, there's no visible vegetation, no obvious signs of water. However, there are clear signs of ancient riverbeds and lakes. Could there have been life on Mars at some point? The primary goal of exploring Mars is to try to discover ancient fossilized microbes, which would be the first discovery of life outside of our planet. We know very little about Mars, or for that matter, about the solar system, or for that matter, about our own planet. Nevertheless, mankind's quest for knowledge and understanding is unquenchable, and will hopefully bring us not just new perspectives, but new eyes with which to view them. NASA's plan for the coming decades is to establish space stations on the surface of the moon with the capability of launching shuttles to and from Mars and to the other planets in the solar system, starting as early as 2025. Let's learn a little bit about Mars. It is roughly half the diameter of the Earth and roughly twice the diameter of the Moon. It is the fourth planet from the Sun and the second smallest planet in the solar system, being larger than only Mercury. It is often referred to as the red planet. The latter refers to the effect of iron oxide prevalent on Mars' surface, which gives us a striking reddish appearance in the sky. Mars is 1.5 astronomical units from the Sun, and it takes about 13 minutes for light to reach Mars from the Sun. It has a 25-degree axis tilt and orbits the Sun every 687 days. It has a 25-hour day. It has two orbiting moons, Phobos, which means fear, and Deimos, which means terror. And scientists think that these two moons are captured asteroids. Mars does have an atmosphere. However, the atmosphere is only about 1% the density of our Earth's atmosphere. 96% of it is composed of carbon dioxide, compared with the Earth's atmosphere, which is composed of 78% nitrogen and 21% oxygen, along with the several trace elements on both planets. Because the atmosphere is so thin, heat from the Sun easily escapes this planet. If you were to stand on the surface of Mars, say on the equator at noon, at your feet it would feel like a spring day, maybe 75 degrees Fahrenheit. However, your ears would feel as if it was winter because it would be 32 degrees Fahrenheit. And that's due to the thinness of the atmosphere. Mars does have polar ice caps in both the north and the south. And both of these ice caps are made primarily of water ice, about 70%. Frozen carbon dioxide accumulates as a comparatively thin layer, about 1 meter thick on the north cap during the wintertime. The southern ice cap has a permanent dry ice cover about 8 meters thick. Now, as shown in these images taken by a Mars orbiter, there is overwhelming evidence that water once flowed freely on the surface of Mars. There are many ancient riverbeds and lake beds. Currently, however, there is frozen water and water vapor on the surface of Mars, but there is no trace of liquid water. Why is this the case? Well, despite the overwhelming evidence, and the fact that there is evidence that there was an ocean estimated to be about 300 feet deep at some point, still we have not found traces of liquid water. And scientists estimate that the surface water dissipated billions of years ago for several reasons. One, there's intense surface cratering, suggesting that much of the water was actually blown away from the surface. Second, some of the water seeped underground and became permafrost. Third, a lot of the water actually became part of one of the polar ice caps. And fourth, As the atmosphere dissipated, much of the water simply escaped into space through a process of atmospheric dissipation. In order to understand this more fully, we should investigate the phase diagram for water so that we can understand the process of sublimation. So what this diagram shows is how and why water changes states between solid, liquid, and gas due to the combined influence of atmospheric pressure and temperature. So if we focus our attention on the line, the blue line, representing the Earth, you'll notice that the y-axis, or the vertical, represents the pressure, atmospheric pressure, while the horizontal axis represents temperature, the two influences on change of state. At sea level on Earth, the pressure exerted by the weight of the atmosphere is represented as 1 atmosphere. And the atmosphere is created by the weight of the air above us, which weighs about 14.7 pounds per square inch. When the temperature is 0 degrees Celsius, which is 32 degrees Fahrenheit, water can transition between solid and liquid. When the temperature is 100 degrees Celsius, water transitions between liquid and gas. That's at 1 atmosphere. Now, on Mars, which is the red bar towards the bottom of the diagram, the atmosphere is very, very thin and therefore exerts very little pressure. So as the temperature warms on Mars or cools, water transitions from the solid state directly to the gaseous state, or vice versa, without transitioning through the liquid phase at all. This process is called sublimation and accounts for why we do not see liquid water on the surface of Mars. The surface of Mars yields some striking features, not the least of which is this large shield volcano called Olympus Mons, or Mount Olympus. It's an extinct volcano in the vast upland region called Tharsis, which contains several other large volcanoes. Olympus Mons is roughly 3 times the height of Mount Everest, and it is either the tallest or second tallest mountain in the entire solar system. In addition, there is a large canyon called Valles Marinares, which is Latin for Mariner Valleys. And it has a length of about 3,000 miles and has a depth of up to 4.5 miles. So the length of Valles Marinares is equivalent to the length of the United States and extends across 1/5 the circumference of Mars. By comparison, the Grand Canyon on Earth is only 277 miles long and 1.2 miles deep. The canyon was formed due to the swelling of the Tharsis area, which caused the crust in the area of Valles Marinares to collapse. In 2012, it was proposed that Valles Marinares is not just a canyon, but a plate boundary where about 93 miles of transverse motion has occurred, making Mars a planet with possibly a 2 tectonic plate arrangement. It has been suggested that Valles Marinares is a large tectonic crack in the Martian crust. And most researchers agree that this formed as the crust thickened in the Tharsis region to the west and was subsequently widened by erosion. The fact that the planet has half the diameter of the Earth and can have both a massive volcano and a massive canyon is referred to as a crustal dichotomy. NASA is currently exploring the surface of Mars with rovers equipped with high-tech gear. Rovers have explored many diverse areas of the planet. Although it has a nickel-iron core, Mars does not have a global magnetic field like our Van Allen belts. An orbiting spacecraft took over 600 million measurements to produce this global topographic map. And the surface roughness map is made using topographic data to calculate slopes across different scales on the surface. This helps to reveal ancient riverbeds and lakes. The thermal inertia map shows resistance to ground temperature change, and that sandy, fluffier terrain has low thermal inertia, but rocky terrain has high thermal inertia. The hematite abundance map, shown here in purple, indicates the mineralogical signature for ancient water on Mars, which appears to have been ubiquitous. This new gravity map, revealing a glimpse into the hidden interior of the red planet, reveals surface tides on the Martian crust and mantle that have been measured. The idea that NASA has come up with is to do extensive surface exploration of Mars. It's prohibitive to send astronauts to the surface of Mars. So instead, scientists have built highly sophisticated robotic rovers that are equipped with very, very high-tech instrumentation so that it can take measures of the surface of Mars and the various systems and send them back to Earth for analysis. Virtually all of the work done on the Mars rovers and the Mars expeditions has been done at the Jet Propulsion Lab, which is located in Pasadena, California, where there is what looks like a small college campus where about 5,000 people work on these projects. And we would say if anybody has the opportunity to go down for a live tour, which is available to the general public, it's a real eye-opener in terms of how science and technology are developed today. If one does go to JPL, one notices that there are a number of specialty labs around the campus, which one can tour. And there are several labs that are devoted to the development of the instrumentation of the Mars rovers and the buildings of the rovers and testing them out and so forth. And there are legions of people that work on each aspect of the rover. And we had an opportunity to visit several times and watch the project develop and build out, specifically in relation to the Perseverance rover. So here it is in about 2015, actually under construction in one of the large cargo bays that they have there. And the rover is large. It's about 10 feet long, not including the robotic arm, 9 feet wide, about 7 feet tall, and weighs about 1.5 tons. So they had to make it with 6 wheels, that each wheel that moves independently so that, it can clamber around on a rocky surface. Remember, it's an autonomous vehicle, And so because it takes light about 7-8 minutes to get from the Earth to Mars, it's not like somebody can drive it using, a game controller or something. They have to take photographs and then generate commands for the rover, upload it, and then the rover proceeds at a slow pace. Now, it's important to remember that people actually work on all aspects of these projects and almost never recognized for the kind of work that they do. So we like to, show a real short film here about project development and work. Another aspect that we had the opportunity to see being built was the heat shield for Perseverance. And as we're heading now into the EDL stage, which is entry, descent, and landing, the heat shield protected the rover embedded in the descent capsule from the intense heat of friction. The spacecraft was moving very quickly, 13,000 miles per hour, and generating a heat of 2,400 degrees. So this space capsule had to have this heat shield to protect it. Now, it's interesting, it's a very complex process of landing this on the surface of Mars. So what we can see in the image on the right-hand side is the rover is nestled inside a kind of carriage device. And above it is something referred to as the sky crane. We'll talk more about that in a second. It also houses a parachute and some fuel and communications, navigation equipment. And below it is the heat shield. So it's sort of like a little space sandwich that is sort of put together. And then this was placed into the payload And you can see this on the left-hand side of a massive rocket, an Atlas V rocket, and launched from Cape Canaveral in Florida. And the journey took 7 months to arrive on Mars. And then the landing took 7 minutes, which of course had to be done autonomously. So that's sort of the setup for the next several set of slides. Now, as we go to explore the landing sequence, each of the components on the left-hand side plays a part in getting the spacecraft to the surface. And it has been referred to, and you can see this sort of poster on the right, as 7 minutes of terror, because the scientists had to give the spacecraft the instructions for landing, but couldn't control it because it takes 7 minutes for the communications to be delivered from the Earth to the surface of Mars, which is done through radio waves, which travel at the speed of light. So once the landing started, scientists really couldn't tell for 7 minutes how things were going. And it was truly one of the most spectacular space accomplishments, technological accomplishments that we've seen. Now, central to this is something called the sky crane. And the sky crane is a device that rests above the rover spacecraft complex. And after the parachute is jettisoned, the sky crane has jets on board, excuse me, which are ignited. And just to give a picture of that, you can see here how the sky crane has cables holding the rover and is sort of levitating above the surface about 65 feet and has a communications cable and very, very gently lowers the spacecraft to the surface, at which point small explosives at the base of the cables explode, and the sky crane then flies off into the distance to burn out any remaining jet fuel because they don't want to contaminate the surface of Mars with anything like that. It's really pretty interesting and complex. I have some actual footage from the flight coming up momentarily. So this is the landing site, which is Jezero Crater. Now, you'll notice that there's an ancient riverbed leading into a large crater. And the idea is that billions of years ago, the crater was a lake fed by this river. And that if there was a chance for life to exist on Mars, it would probably be in this aqueous environment. So the idea was to land in the delta area and then explore it, drill into the surface, take samples, and see if we can make some headway on the possibility of finding ancient fossiled microbes. So that's sort of the setup for the project. And then after that, we would explore some of the highlands and other areas. So to put this in perspective, on the left-hand side was the image as we landed on Mars, which was in just about a year ago. And on the right-hand side is what it's presumed to have looked like in the past. So that's not an actual photo, that's an artist rendition. So let's take a detailed look at the landing stages and what was involved. The first stage had to do with jettisoning the support craft to lighten up the vehicle and start to steer towards the pinpointed location of the landing. I have some video of some of these things. So you'll notice here what it would have looked like as the spacecraft entered the atmosphere and the heat shield was activated. As mentioned, I mean, the heat of 2,400 degrees is pretty intense, but the shield held up, very, very nicely. And in addition to being a heat shield, it's an air brake. So although the atmosphere is only 1% that of the Earth, it's still enough to slow the craft down. Remember, they can only be going at a very, very low speed, not even a mile per hour in order to have a successful touchdown. So the heat shield is also an air brake. And here it is, what it would look like going through the atmosphere at about 13,000 miles per hour. You generate like tremendous amount of heat. But it's slowing it down rapidly from this 13,000 mile per hour speed to around 200 miles per hour. It's still pretty fast. So while this is occurring, we have to activate the guidance system. They have an advanced guidance system so that we can have a successful landing, because there are all kinds of different variables. So as we start to enter, the craft itself starts to take all sorts of readings of the environment so that it can start to approach this specific target area. Even if it's off by, a mile or two, that'll have a tremendous impact on the mission. So this active guidance system allows the spacecraft to move from being a spacecraft to basically an aircraft that is going to start to steer itself. And you'll notice here what that would have looked like. So it's got various jets in the capsule that are starting to steer in particular direction. You can see in the center of the image, there's a picture of Jezero Crater, and it's like basically coming into an airport. Now, right about here, it's necessary to deploy this supersonic parachute. Underwent a lot of testing. It's about 70 feet in diameter or so, and it was deployed about 7 miles above the surface. And the spacecraft would have been traveling at about 950 miles per hour at this point. And so you can see how it's deployed and radically slows down the speed of the craft. So fortunately, the atmosphere of Mars gives us a little bit of tactical advantage for the landing. Now we've got this really interesting system called radar lock and terrain navigation. And so basically, while it's drifting lower, the spacecraft takes images of the area that it's going to land towards. And as it descends, there's an onboard computer that has images that were taken by orbiters of this area. And it starts to do a comparison between what it sees and what it has on its computer database to try to mesh those two images and gain a lock on the landing site. So take a look at that. And you'll see as it's descending here, takes all kinds of reading and then compares right, left, which are images and also pictures in the database. And it starts to sort of narrow exactly where it needs to go. Now, at this point, we're at the point where we're going to jettison the parachute, and that will activate the jets on the sky crane, which will bring the whole assembly down to about 20 meters above the surface of Mars, and then very gently lower it onto the surface. So let's take a look at that. And you can see it here coming in, and then the sky crane itself drops out with the rover on the base and activates its jets and steers right over the pinpoint of where we want to touch down. You'll notice it actually lowers using cables, drops it right onto the surface, activates explosives to release the cable, and flies away, leaving the rover on the surface of Mars to actually wake up and start doing its scientific work. So, this truly is one of the most spectacular things a student has ever seen in terms of technological space maneuvering. And it's being perfected so that it can be used in other locations, on other moons, and other planets at some point. This is a smashing success. So while all this was occurring, there were actual cameras on the spacecraft showing real live footage as it occurred. So let's take a look at that.
About 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely.
So now that the spacecraft has landed on the surface of Mars, it can actually take a selfie of itself, composed of several images that are stitched together to form a picture that scientists use to observe the state of the spacecraft. So clearly that the spacecraft is in good shape, and scientists are then encouraged that they can start the next steps of the process. The spacecraft is powered by a nuclear generator, a small nuclear generator that uses plutonium-238. And this allows the spacecraft to generate its own electricity that will power it for at least 14 years. The motto of JPL is "Dare Mighty Things." And in the background, we see an image of New York City. That's the New York Empire State Building that's lit up red in honor of this tremendous accomplishment. And the motto, "Dare Mighty Things," is really a way of inspiring scientists to do what seems initially to be impossible. And given the amount of brilliant work that they've done through the decades, which is inclusive of the Voyager missions to the outer solar system, missions to Jupiter and the moons of Jupiter, and many others, Earth-orbiting satellites, we would have to say they're living up to the motto. Now, the motto is taken from the writings of Theodore Roosevelt, who was the 26th President of the United States. And it says, "Far better it is to dare mighty things, to win glorious triumphs, even though checkered by failure, than to rank with those poor spirits who neither enjoy nor suffer much, because they live in the gray twilight that knows not victory, nor defeat. Now that we've landed safely at Jezero Crater, and all of the instrumentation seems to be functional, let's take a tour of the crater and see what it actually looks like on the surface of Mars from the perspective of the rover.
This enhanced color mosaic from the Perseverance rover on Mars allows our team to walk right into the scene in Jezero Crater. This is a combination of images taken by Mastcam Z, so it's incredibly rich in detail. The blue sky is an indication of the enhancement we have done to the image. If you were on Mars, everything would appear pink, including the sky. By enhancing the image, we make it easier for the science team to use our everyday experience to interpret the landscape. The mountains that you see in the background are the rim of the crater. They're more than half a mile high and about 6 miles away. That canyon was carved by a river about 3.5 billion years ago, when the climate of Mars was very different from today. The cliff-like brown hills you see here are more evidence of that river. These are part of the delta. When the river hit Lake Jezero, its mud and sand were deposited on the crater floor. One of the most scientifically interesting aspects of this mosaic is this whitish area here, which the science team has been calling the bacon strip, based on its appearance. We think this is a layer of mud deposited on the lake bottom, now turned to rock. That mud layer is important because it may be the best place to look for evidence of Martian life that could have lived in Lake Jezero. The large boulders on the delta are another interesting target for investigation by Perseverance. The boulders very likely washed down from far up the river channel, from places too far away for the rover to ever go. They're a gift that allows us to learn about what's far beyond the crater. As soon as we're done with our investigation on the crater floor, on smaller rocks like these, which we think are volcanic, we'd like to move quickly to the delta. But unfortunately, Perseverance has to take a longer route to avoid these sand dunes. Mosaics like this one help us learn more about the ancient Martian environment and provide new clues to where to seek evidence of ancient microbial life. We're just getting started on our long journey through the crater.
Given the rough and rocky terrain of Mars, late in the project, scientists started to consider whether or not we should build a helicopter to help with the investigation. Of course, the challenge is that there's a very thin atmosphere, and how could we make something small enough and light enough that would actually work? So they were actually able to build something. They named it Ingenuity. It's very small. It's only 19 inches high, and the rotors are 4 feet in length. And it only weighs 4 pounds. It's charged with solar power, and because these are autonomous instruments and vehicles, it's self-recharging. It communicates wirelessly with the rover, which sends the signal to the orbiting satellite, the Mars Surveyor, which sends it back to Earth for analysis. And we'll actually see some footage in a moment of the spacecraft Ingenuity flying on the surface of Mars. It has to generate 2,400 revolutions per minute in order to fly in the thin atmosphere, and has onboard computers, navigation sensors, and even a couple of cameras. So in this slide, we can get a very clear view of Ingenuity, the helicopter, and we could see the solar panel on the very top of the craft, as well as the rotors. There's double rotors in order to maximize lift, which are about 4 feet long. And you can see the overall workmanship of the helicopter and the extreme miniaturization that was required to create something that would fly and still only weigh about 4 pounds. This has been a very successful mission. You can see the little telescopic view on the side that there's a picture of Ingenuity on the surface of Mars. So here we have a nice clear picture of the Perseverance rover with the Ingenuity helicopter right alongside it. And because the information on the helicopter, be it photos or video or any data that it may collect, has to be communicated back to Earth, it has to send this information wirelessly to the rover. The rover then communicates it up to an orbiting Mars satellite, the Mars surveyor. And the surveyor sends it back to Earth for observation and analysis. And this is all articulated using the Deep Space Network, DSN, which we'll talk about in a little bit. So let's go observe the first flight on Mars right now, and we've included the sound of the rotors on Mars, so you might want to turn up your volume. So there you have it, the first successful flight. Since that time, Ingenuity has made about 18 flights, the longest of which is about 1.5 miles, a little more than that, and so far has been a spectacular success. The technological advances presented by this mission are truly astounding. However, we need to remember that the technology exists to serve the science goals of the mission. The 4 primary goals are, first, to identify past environments that might have been capable of supporting microbial life. This is referred to as astrobiology, which is the study of the origin, evolution, and distribution of life in the universe. Goal 2 is to search for signs of possible past life, or biosignatures. This largely will be sought out using core samples of rocks, which we'll talk about next. Goal 3 is to collect these core and rock samples, store them, and transport them back to Earth for analysis via a future mission. And then Goal 4 is to start to prepare for future human exploration of Mars through the production of oxygen, which we'll talk about in the instrumentation section of the presentation. Central to the success of the mission science goals is the ability of the rover to collect and store core samples of rock collected from various locations. This involves a very sophisticated process of carefully selecting, drilling, and handling the samples. So on the right-hand side of the screen, you can see the coring bit, and on the bottom left-hand side, the mechanism is housed on the end of the crane arm, which is used to drill into the rock. In the upper left-hand corner is a picture of a rock from which a core sample has been extracted. And the hope is to extract about 46 samples that will eventually be returned to Earth. So now let's hear from a mission scientist about how this system was developed and the complexity involved.
In terms of robots that go into space, the sampling and caching system on the Mars 2020 mission is the most complicated, most sophisticated thing that we know how to build. This is the system that allows us to take core samples of rocky material on the surface of Mars, carefully seal them in very sterile, clean vessels for eventual return to Earth. We've been working on the sampling and caching system for 7 years, and that's because it's a tough job.
We're testing the equipment to make sure that it's going to work when we get to Mars. It has to function on its own. We have to think of all eventual possibilities and try them here first. And then if they don't work, change it now because we can't make any changes later.
To drill into the rock on Mars, pull out intact core samples, seal them hermetically, and to be all done autonomously by a robot hanging off the end of a rover on the surface of Mars has been a challenge. We've got actually 3 robots necessary to do the sample and caching system. Our big robotic arm out on the front of the rover, that takes our drill, pushes it against the surface, and allows us to take core samples. Then we put that core sample in the bit carousel, the second robot that takes that from the robot arm and puts it down inside our adaptive caching system. This is the part of the sample and caching system inside the rover. We've got a little tiny robot, a special robot arm called the SHAW, the sample handling arm. It takes the samples out of the bit carousel and moves them through volume assessment, image taking, and eventually to sealing, and then replaces the cylinder containing the sample in a storage spot, all on its own in the matter of a few hours. We have designs on bringing them back in a decade. Mars has been at the fore of our consciousness about the questions of life. Could life exist in one of our nearest neighbors? I think we have a lot to learn, life or no life, about the evolution of our solar system, about our planet, by looking in depth at rocks brought back from Mars.
So here we can see the samples that have been taken so far, and they include both core samples from rocks as well as just soil from the surface. And the hope is to take about 45 different samples from around the surface of Mars for their eventual return to Earth for further analysis. So now we'd like to proceed to the 7 primary instruments on board the rover. Robotic senses are science instruments, state-of-the-art tools for acquiring information about Martian geology, atmosphere, environmental conditions, and potential biosignatures. Towards this goal, it is worth considering these 7 primary science instruments on board the craft in some detail. Take into consideration that each instrument was designed by a team of people that had to make the instrument effective, but also lightweight, strong, invulnerable to radiation, durable, and able to synchronize with the existing systems on board the rover without any form of interference. Most of these tools took years to develop. As mentioned, we have visited JPL a number of times, and on one occasion had the opportunity to visit the Mars Yard. It's a simulated Martian surface where there is a duplicate rover, and this rover is used to troubleshoot issues that may arise on Mars, but also to run through routines over rocks and various things to test the capability of the rover in preparation for various experiments that they wish to run. We were really impressed by the size, the complexity, but also the workmanship of the craft. Because there's a limit to how much space and weight they could put on the rover, the systems are extremely dense and complex in nature. And since each thing was developed by a separate team, putting them together to, work harmoniously took a fair amount of testing and maneuvering. And so far, everything has worked extremely well. Now, it is mission critical to obtain high-definition photos so that scientists can adequately select areas of interest for further investigation. Most of what we see in the media is produced by what's called Mastcam Z. Z stands for zoom, and it is a camera that's capable of clearly detecting objects the size of a paperclip, say at a distance of 100 yards. It also has stereoscopic and panorama capabilities. The image in the background of the slide is a sample of what Mastcam Z can do. Secondly, there's an instrument called the SuperCam. It's a laser micro imager. And you can see the instrument in the bottom right-hand corner of the slide. And on the left-hand side, a sample of the kinds of things that it would be looking at. And the SuperCam does have a camera, but it uses a combination of lasers, infrared, and close-up photos to analyze the geological features of Mars. Now, I'd like to call in a JPL scientist to help us understand this tool a little bit more.
So SuperCam looks out of the big circular window in the white box on top of the mast, and it uses spectroscopy, which is just when light excites atoms in a rock and we get unique shifted wavelengths back to us. And so we use a combination of lasers and infrared vision, and that lets us do science even further out than the robotic arm. The lasers reach 7 meters or 23 feet away, and the infrared much, much further. And that's not even all. We have a tiny high-resolution camera and a microphone to hear Mars. And that's how we heard the helicopter.
And can you talk about some of the images SuperCam has taken and why they are important to scientists?
Absolutely. So we started by taking out images and spectra near the rover. And as you can see in this image, the laser actually blows away the dust and makes these small pits in the rocks. And that lets us analyze material that's just below the surface of the rock, which is what we care about. And then we can record the sounds of the laser with our microphone, and it tells us something about the hardness of the rocks. And then starting Sol 26, we were able to take pictures of these long-distance targets like Kodiak, and that really helps the rover team understand where to drive next for more close-up analysis. And these red circles you see is actually the infrared telling us about the mineral content of these far-away outcrops. So that's how SuperCam figures out more about the geological history of Mars, and we're so excited to see what the laser can do.
This composite image of Jezero Crater's Delta Scarp was generated using data from the SuperCam and the Mastcam Z in combination. The images reveal that billions of years ago, when Mars had an atmosphere thick enough to support water flowing across its surface, Jezero's fan-shaped river delta experienced late-stage flooding events that carried rocks and debris into it from the highlands as well as outside the crater. So this next instrument, MEDA, is the Mars Environmental Dynamic Analyzer. And it makes weather measurements including wind speed and direction, temperature and humidity, but also measures the amount and size of dust particles in the Martian atmosphere. And it is located on the mast. The next instrument for consideration is called MOXIE, Mars Oxygen In Situ Resource Utilization Experiment. And this instrument is designed to produce oxygen from the Martian carbon dioxide atmosphere for breathing, as well as creating liquid oxygen rocket propellant Since one of the science goals for the mission is to prepare for human exploration of the planet, it is necessary to find ways to supply oxygen. MOXIE is designed after trees and plants because it takes in CO2 and exhales oxygen. Next is PIXL, the planetary instrument for X-ray lithochemistry. So to measure the chemical makeup of rocks at a very fine scale requires X-ray lithochemistry. And what it does is seek changes in textures and chemicals in Martian rocks and soil left by ancient microbial life, and is guided by an artificial intelligence system. PIXL is used at night because the temperature on Mars fluctuates more than 100 degrees on any given day. This causes the robotic arm to fluctuate more than a half an inch in length, which can easily cause distortions in the measurements of the instrument. Therefore, PIXL is often referred to as a night owl. Since one of the mission goals has to do with astrobiology, PIXL is crucial in assisting that end. And here is a photo of the night owl at work. Our next instrument is referred to as RIMFAX, Radar Imager for Mars Subsurface Experiment. And this instrument has ground-penetrating radar, which can detect subsurface features up to 30 feet, which could include ice or large rocks or objects under the surface. And it's similar to what's used on Earth, say, for examining areas around the pyramids or other archaeological sites of value. Sherlock, the scanning habitable environments with Raman and luminescence for organics and chemicals, is an instrument for searching for the basic chemicals necessary for life. Sherlock focuses upon fine-scale detection of minerals, organic molecules, and potential biosignatures. It uses an ultraviolet laser light to spot organic chemicals in much the same way that modern crime scene investigators look for forensic clues. When an ultraviolet light shines over certain carbon-based chemicals, they glow, much like material beneath a black light. This glow can help scientists detect chemicals that form the presence of life. Using Sherlock, scientists were able to detect a specific cycle of seasonal methane, which expires from the surface of the planet on a cyclical basis. Given that so much information and data is being generated by the rover, how is all this information sent back to Earth so that scientists can examine it? And to answer that question, we need to explore something called DSN, the Deep Space Network, which is designed to receive signals and send signals to distant spacecraft. Now, it's necessary at any time to have a large receiver or a dish pointed in the direction of space from which signals are being sent. And since the Earth is continually rotating, it's necessary to have 3 large dishes. And signals from Mars are received on Earth via one of the 3 large antennae located in California, Australia, and Spain. As the Earth rotates, one of the antennae will be pointed towards Mars. The diameter of these dishes is 70 feet across, which yields a total area of 1 acre. Not only do these dishes receive data and information from spacecraft, but scientists can also send commands to the spacecraft using the same technology. Radio waves travel at the speed of light and take about 7 minutes to reach Mars. Once the information is received via the Deep Space Network, it is forwarded directly to the Deep Space Control Unit, which is located at the Jet Propulsion Labs pictured.
Touchdown confirmed.
In the 10 months since the rover has landed, we've been busy, and it's been a year of perseverance. From operating during COVID to the challenges we experienced with sampling to interpreting the scientific results. It's such an appropriate name for the vehicle, but also for the team and the mission itself. This mission has a series of firsts that will help future generations understand more about our solar system. One of my favorite moments was seeing our first rock core sample, looking down the tube when it was still in the drill bit and confirming that it was indeed a success. Now that we've collected the samples, everyone wants to know when and how they'll be coming back. We can't wait for the future mission to pick them up and ferry them to Earth to analyze if any of them show signs of ancient life.
The first flight of a powered aircraft to another planet.
Another highlight of this year was working with the helicopter team to deploy Ingenuity and experience the first powered flight on another planet. It was so amazing to see the team adapt to the environmental changes in order to keep flying. The helicopter has become a real asset and partner to our science team. It feels great to be part of making history. What motivates us as engineers and scientists exploring another planet is the opportunity to continuously learn more. Now that we've toured the floor of Jezero Crater, we look forward to investigating the Delta, a part of the crater where a river fed into a lake in the distant past. It's almost as if we're starting a new mission because we'll start to cover new ground and make new scientific discoveries. What I'm most proud of is the team. How we operate the rover, overcome challenges, and the dedication that everyone brings to their job each and every day.
All right.
One we haven't really talked about yet is why Mars?
Yeah, so the Mars we know today is a barren, dry, very cold landscape, not particularly hospitable to life as we know it. But we know, based on our observations of Mars from rovers and orbiters, that Mars wasn't always like that. And Mars was once very Earth-like. And we think that there's a good chance that Mars was capable of supporting life just like early Earth was. And the period of time when Mars, we think, was once habitable was the same time that life was emerging on our own planet. And so we think Mars is a really attractive place to go to look for signs of ancient life, and perhaps the best place in the solar system to look for signs of ancient life. And every rover mission we've sent to Mars has found and discovered and explored habitable ancient environments. And so we think Mars is really a great place to go to look for signs of life beyond our own planet. And The really neat thing and fascinating thing about studying Mars is that in some ways it is so familiar, particularly when we look at ancient rocks and we recognize the kind of environments that we know and see here on our own planet. Yet this is another planet, and it took a very different path over time to look the way it does now. And so there is still something alien about it. And so it's this combination of the familiar and the unfamiliar, and that makes Mars such a fascinating place to look at and to study and to understand.
Tony Oranges on YouTube wants to ask you 2 questions. What new upgrades would you want to see on future rovers on Mars? And also, how many years can the Perseverance rover survive doing science on Mars?
Okay, I'll start with the second one. It's actually not an easier one, but it's one where we build the hardware. It has sort of a warranty, just like your car has a warranty, for about 3 years. We test it to all 3 years, but we have enough energy. We expect the hardware to work a lot longer. You can see with Curiosity and with Spirit and Opportunity, all of our rovers have outlived their lifetime. So the 3 years is when the warranty expires, but we expect it to live quite a bit longer. We're confident of that, but we're also humble about the fact that, different things can happen. So we hope to have it, live a decade or longer, just like Opportunity. Those are great, great missions. And as far as things I would like to see, when I very first started this mission in 2015, because we had this autonomy focus, I remember going into the conference room with the team and I said, we got it. We can't just code this thing from the ground, which is sort of what we do. We write our sequences and send them up every day. We need this thing to be more autonomous. And I put my feet up on the table and I said, here's what I want. And I pushed the button and I said, do a great science mission and it'll be done, right? And so we're not anywhere really close to that, but getting the rovers onboard autonomy, onboard sensing so that it can choose its own science targets. We're toe dipping into that one. I think our autonomous navigation is very fast, but it is not quite at the limit of what the wheels could drive. So we could still drive faster. Our next missions are getting really close to pinpoint landing. So that's a great one. But then just this idea that the Percy figures out what she wants to do every day to accomplish the science mission that we've given her. So those are my dreams.
The main question we're getting a lot right now through our chats and our audience watching at home is, what are the biggest surprises that we've gotten from this first year on Mars?
Yeah, and this is a great question for me because I and many scientists who've thought about landing sites on Mars, we spent years poring over those orbiter images, trying to guess what's there and try to interpret what's there. And so going into this mission, I thought, I've thought of all the possibilities, and it's going to be one of those things that I've thought about, and that's how we're going to explain the rocks. But of course, Mars throws us surprises, and we certainly had that. One thing, thankfully, was not a surprise. And if we bring up slide 12, we thought from orbit that there was a lake and a delta, and you just saw that in the video. And when we got on the ground and we imaged towards the delta deposit, we saw this beautiful outcrop. And this is the kind of outcrop that you would bring a geology class on Earth to teach them about deltas. This is classic delta stratigraphy, and you see the layers in this image. The flat layers on top represent the upper part of the delta going into those dipping beds as you get into the lake. And then as you get into those flat beds at the bottom, those are the layers that we look at for signs of preserved organics and possible signs of life concentrated there in the distal parts, the distant parts of these lake deposits. And so we were relieved that this was not a surprise. There is indeed a delta. We have confirmed it, and we have beautiful outcrops to show that we have this habitable surface environment preserved in Jezero. But there were still surprises in store. So if we bring up the next slide, slide 13, while we knew there was a lake and a delta here in Jezero, one thing we weren't expecting was signs of pretty active high energy flood deposits. And so that's what we're seeing here. This is an outcrop from the front of the delta, and that arrow there points to a big boulder, and that's an almost 1 meter wide boulder. And so in order to transport a boulder like that and the boulders in the surrounding outcrop, you need pretty high energy, energetic floods coming into the crater. And so we didn't know that was happening here in Jezero. So we think we had this lake and this delta setting that transitioned over time into something much more energetic and perhaps catastrophic. And that might have been how water had its last gasp here in Jezero crater. If we bring up the next slide, while we had views of the delta when we landed at Octavia E. Butler Landing, seen here again in the orbiter image, we actually landed on the rocks of the Jezero crater floor. And we weren't sure what to expect of these rocks. There were different hypotheses thrown out by scientists. Are they igneous or volcanic rocks formed from magma or lava flows? Or were they sedimentary rocks? After all, we are in a sedimentary basin where we knew a lake was present. And so we have this question. And in this case, the orbiter data doesn't tell you the whole story. So we went into this thinking, you could probably split the team in half, those who thought it were going to be igneous and those who thought the rocks were going to be sedimentary. So the first couple of months of the mission, we were left scratching our heads about this question. The rocks weren't giving us many clues. They were dusty. Their natural surfaces were obscuring the kind of textures you would typically use to interpret the origin of the rocks. But by the time we got down to the location marked here at Rubion, which Jennifer talked about, the first place we took our sample, we had the opportunity to actually scrape through the natural surface of the rock to see what lied beneath. And so if we bring up the next slide, this is our first abrasion. And Jennifer mentioned that these rocks have interacted, have been altered and weathered. And that's exactly what we saw here as well. You can see those holes, and those are holes in the rock, and not just caused by wind particle or sand particles blasting the rock. These are actually inside the rock, suggesting that water has moved through this rock and eaten away parts of that rock. But when we looked at this texture, this variation of light and dark minerals, this is pretty diagnostic and conclusive for an igneous rock. And we think it was formed by volcanic lava flows. And so the other neat thing about this, where we start to think about habitability and astrobiology potential, is that some of those light colored minerals you see there, those are salt minerals. And those only form by precipitating out of water moving through these rocks. So while we don't typically think of volcanic or igneous rocks as the prime place to look for signs of ancient life, at least here on Earth, given that water has moved through these rocks, there might have been habitable niches in this rock that capable of supporting signs of ancient life. And so that's pretty exciting to find igneous rocks here. Those are great rocks to get age dates from and learn about processes in the interior of Mars, as well as to have this potential habitability aspect of these rocks as well. And so really exciting to have this kind of discovery. And to answer that question, volcanic or sedimentary, we answered that in the first year of the mission.
It's good to know the rover's doing just fine up there after its first year.
I will add one, I'll speak for Ingenuity. We've kind of, brought Ingenuity in. We're the communication relay station for Ingenuity. And in January, when we were going through this issue with the pebbles in the bit carousel, we had kind of non-standard dust storms. And those dust storms they put some dust on our HAZCAMs, and they put some dust in Ingenuity's rotors in a way that the next time we tried to spin those rotors, we saw that we had more drag than we intended. And so we actually had to clean those out a little bit so that we could keep flying Ingenuity, but they're clean now, and we just finished another flight. So it's looking good as well.
Well, thanks for that update as well. How did you know they were asking about Ingenuity in the chat as well? So thanks for the update on how she's
everybody
working with the
loves
rope.
Ingenuity. Yeah.
So Katie, I'm going to throw this one to you. We've gotten quite a few questions about the Mars sample return mission. But this one in particular is from Jordan on LinkedIn, who wants to know, what would the procedures be to prevent contamination of off-planet samples once they are brought back?
That is a great question, and we have a whole branch of NASA that thinks about that. That's called planetary protection, and it's something that we take very seriously. And it starts to cross into the realm sometimes of science fiction, but again, it is something to take seriously, and something we think about when we bring samples from another world and a world that could possibly support life and that we know or that we don't know. And so when we think about bringing samples back to Earth, we talk about biocontainment facilities and having the kind of facilities and laboratories here on Earth that we use to treat the most sensitive biological things here as well. And so that's the kind of facilities that we would develop and that NASA is working with its international partners to develop to support and house those samples when we get them back. So that's something that NASA and its partners are looking at and looking to develop to make sure that we stay safe and that the samples are safe as well.
There's been lots of questions, so thank you all so much who have tuned in and asked your questions in the chat tonight. This one is for both of you, but I'm going to have Jennifer start us off. Summer on LinkedIn asks, so many cool things are going on. What would you tell a STEM or creative student who really wants to work at NASA? Things they should know. Also, did you always want to work at NASA?
So I'll start with the second part because I'm actually a farm girl from Ohio, and I spent my summers as a teenager in the fields. Sometimes I was weeding the bean fields, and I was painting the barn roof, and all these great things. And so I didn't necessarily see myself as a NASA engineer. However, my dad had worked in the missile industry back in the Nike Zeus days, and he had some really cool stories, and I just thought, oh, that sounds adventurous. So I ended up going to MIT and getting a job at JPL, which I just thought was the coolest thing. And so, with that background, one thing I will say is if you work hard and are passionate about what you're working hard on, and you just, you persevere through your challenges and you have ingenuity on the things you're trying to solve, you could be a farm girl from Ohio who didn't know what NASA was, and you can be the project manager of the Perseverance rover. So there really are no limits. And then the other thing I would say is, just try different things. There are lots of ways you can be involved in the program and working for NASA and these missions. You can, get into the science like Katie. You can do the engineering and autonomy like me. You can do the media and outreach, right? Like Brian and the other folks here. There's and videos and taking all these images and doing productions. And even we have this great partnership with Hollywood where, they help take our messages a little bit more clearly to the public than sometimes we can do. And so, I don't know what part of it you'd like to do, but there are so many options and opportunities for you to be a part of exploration.
Part 2 of this series will focus upon learning how to understand the delicate systems of our planet and how to harmonize with them through deeper understanding aided by science. Specifically, we will discuss how modern satellite technology can give us new eyes with which to focus upon planet Earth. Part 3 of this series will focus upon the newly launched James Webb Space Telescope. Using infrared technology, the telescope will be able to peer through the cosmic dust and collect images of the very first stars and galaxies that formed at the beginning of our universe. It will also be used to study the planets, black holes, exoplanets, and dark matter.